In the first part of section 12.4, we studied the linear supported vector machine, which works for separable data sets. What if the data set is inseparable? As in this figure, for example, some points from these O points, and one of them is here, and from positive points, one of them is here, so that we cannot build separating hyperplane. So there is no feasible solution for the linear supported vector machine. To fix this problem, we allow the algorithm make mistakes. For example, for these points and for those points, just the points are either inside the strip or the other side. And by introducing select variables, we can do it. Okay, let's see the formulas. But here, the new formulation involves the select variable. It allows some instances to fall up the margin, but penalize them. So we are allowed to make mistakes now, but we pay a price. Okay, we'll introduce a select variable, and such SVM supported vector machine is called the soft margin classification. So it is relating, it is involving some cost penalization. Let's recall the original linear supported vector machine. It is given in this way: minimization of the norm squared of the weights and subject to these constraints for each point. Now, the corresponding soft margin classification can be formulated in this way. We introduce select variable, and then now the summation of these select variables as part of the objective function, and the same the left-hand side, and then we put over there now, okay, that is originally 0, but rather than 0, we are putting here minus psi I, so that, but now that is non-negative. Along with this one, it is in a sense a sort of a cushion is added. So here, that's the formulation for soft margin. And for example, now C is a sort of the controller, but once C is large, that means the select variable should be smaller. In this minimization was large over there, then the other part must be small. For large C, now the select variable becomes small, so that here we can find such the strip, and that strip is along with the maximum possible margin. But once the C is small, then we allow the select variable become large, so that along with a large cushion, the strip will be built. So here we have the result, and along with one point at the other side. So by changing the parameter C, we can here control the tightness, or now that is a sort of bias or variance trade-off, and that C works as a parameter and user parameter. Okay, now here the constraint allow some select of size psi I, but we pay a price for it in the objective. As you can see in the formulation, here the select variable was variable is large, then the cost becomes large, right? Okay, if we have that, and then now psi is 0, so the penalty is 0. So for the points in the right side, and we don't have to have a positive select variable. And otherwise, now here, otherwise, now that means that now price is positive, so that eventually, and because and this equation must be satisfied once it is the other side, so that we pay the price psi I, positive value. Okay, here we have this derivation. Psi I is 0 when the given point is in the right side, but otherwise, then the psi, the select variable, will be positive. Okay, so it's same as this one, so that out of this now 1 minus that, and we try to choose the maximum because it's 1 minus. Okay, there's 1 minus now this quantity, and now by taking the maximum compared with 0, we have that one, and then here, okay, once it is positive, we take this one, right? Okay, so the objective function can be written in this way, and rather than psi I, we change it this way, and then for this problem, we now try to solve the problem, this one, and along with the Lagrangian multiplier taken in. And Lagrangian is formulated in this way. And then here it is original one. Then this portion is now here from constraint. And also for this select variable, again, we have a Lagrange in term, extra term. Okay. Now, this is Lagrangian. Again, the original problem, primal problem, will be the same as min-max of this Lagrangian. And its dual problem will be max-min. And the mean part, if you do the similar the calculus, then along with the corresponding KKT conditions, then you can formulate the dual problem. This is a max part, and mean part can be changed in this form along with this constraint. The only difference from the original linear SVM is this one. In linear SVM, it is required Lagrange multipliers must be non-negative. Now, extra condition for soft margin classification is this one. Here, alpha I must be less than or equal to C. Only this portion is additional in solving the dual problem, so that now we can implement the algorithm quite nicely, only considering this as additional part. So it's quite neat in mathematical formula. So basically, the original linear SVM and this soft margin classification, they are really almost the same. Only difference is this one. Okay, so you can implement the soft margin classification very effectively. Also, the same strategy can be used. You have to take care of this portion, but except to that, everything else is the same. Okay, here we have algebraic expression for the dual problem. we define this Z metric, and along with the multiplication of the label and the point, okay, collection, and then all one vector, then the dual problem can be written in this way. Okay, that is now here. Now alpha dot 1. So basically this is a summation of Lagrange multipliers. And then now we call this Z transpose, that is called gram metric. And each entry can be found in this way, along with this dot product, ith1, jth1, and also label for xi and xj. This whole product is the entry, ij entry of the gram metric. And we can write in this way in the metric vector format. And we can solve this one again quite easily by using some quadratic programming technique, and or as in the previous one, and SVM can be used to solve this problem. Here we have a summary of supported vector machine. In training, we start with computing the gram metric, and we have to solve the problem by using a technique from quadratic programming or SVM. And after finding the optimal values of alpha, we can compute the weight, and by using the first KKT condition, and by considering only positive side, and we can decide the double zero in optimum. And when we try to get classification for a new point x, then now we compute for each point and the value dot product, and then here we try to find this evaluation, and now we try to decide the sign so that we can classify positive side or negative side. That's the summary of supported vector machine, either for either linear supported vector machine or for soft margin classification. Only the difference is just we have upper bound for alpha I, and then here C, okay, that portion. Except to that, everything else is the same. So for inseparable data set, you can do good classification. Okay. Now here, why are supported vector machines popular in machine learning? That is, now, margin. We try to maximize the margin, and eventually it will reduce overfitting and also enhance classification accuracy. So it is better generalization. Now, for nonlinear later on, in the third part, we'll consider nonlinear expansion of the supported vector machine. That is, along with future expansion. And the future expansion is we try to map the point into a high dimensional space. And now here we can classify some inseparable data sets. And however, we don't have to do explicitly by using some trick. We can avoid some complicated computation, and which is called the kernel trick. By using these techniques, the SVM, the supported vector machine, becomes quite powerful and also flexible. So supported vector machines are quite popular in machine learning. Okay, that's the end of the second part, and we'll continue in the third part, and we'll deal with nonlinear supported vector machine. Thank you.